So we tried to quantify this empirically as something we call the radial acceleration relation. As we noted, if you have all these different rotation curves, we now have 3 different galaxies, one with a big central bulge, one is sort of mostly a spiral disk, and one of these low surface brightness galaxies. And you can see the rotation curves look very different, right? The central bulge sort of explains the rotation of the inner few points, but then it flattens out and fails in the way we see over and over and over again. The same thing for the spiral galaxy, but as we get to a low surface brightness galaxy, you don't explain really any of that. Nevertheless, you can plot other things. This is the centripetal acceleration, just v squared over r. That's the force per unit mass that is required to keep a star in its orbit. And along here is what Newton predicts for that quantity just based on the baryons that we see. And so if there were no dark matter or any funny business, all the data would follow that dashed line. Those 2 quantities should be equal. But you can see they bend away, but they bend away in a way that is the same for each galaxy. They just occupy different parts of this. So now we can pile up all the galaxies that we know about into this density diagram. There are now over 150 individual galaxies, and you cannot really distinguish the difference between them. So there are about 2,700 individual data points along the rotation curves of 153 galaxies here. And they all, within the errors, pile up on top of each other. So again, this is what Newton predicts for what we see on the x-axis, and on the y-axis is what we get. So if there were no funny business, this would be a straight line. But what we get is related to what we see. It's not the same, but it's related. And so you can predict this from that. And this bends at a critical acceleration scale of about 10 to the minus 10 meters per second per second. It's about 1 angstrom per second per second. Tiny, tiny, tiny acceleration, but that is what stars feel in their orbits, in their galaxies. And we only really run into this dark matter problem near these very low acceleration scales. So this is sort of the amplitude of the discrepancy, i.e. how much dark matter we need relative to the normal matter as a function of acceleration over everything I could think of. So you are here. This is the sort of 9.8 meters per second that we live with on the surface of the Earth. Here are some very high acceleration systems. The last orbit of emerging pair of black holes, the first source detected by LIGO, the Gravitational Wave Observatory. What you expect for the surface of a neutron star that is itself on the brink of collapse into a black hole. Gravity works fine on all these scales, works fine in the solar system, and it's not until you get to these extremely low accelerations that you start to see a discrepancy. Now this behavior was predicted by a theory called MOND for modified Newtonian dynamics, introduced by Monty Milgram. So let's chase up the other side of this tree, because it really is, a lot of the data are ambiguous. Some favor one branch or the other, but really all you know is that something is wrong. The gravity we know about applied to the stuff that we see doesn't explain the universe. So maybe it's not dark matter, maybe it's some modification of the equations. And so here is the idea is that, you know, our brains usually think, oh, well, galaxies are big. And so on some large size scale, the force law will change. And that's not how it works. Well, the scale that matters is not some giant length scale, but it's this tiny acceleration scale. So above this tiny acceleration scale, everything is normal. Newton and Einstein can do everything for you without dark matter. Below this scale is where we need dark matter, or this modification, which is just this craziest thing to look at. You just compute things as you would for Newton normally and multiply it in quadrature with this new constant of nature that just makes your head explode if you know any theory. Nonetheless, when it first became aware of it, and this was the mid-90s when I even first bothered to read the original papers that Milgram wrote, back in 1983. And I really noticed this line. He said, disk galaxies with low surface brightness provide particularly strong tests. In 1983, most astronomers believed in something called Freeman's law, which asserted that all spiral galaxies had the same surface brightness. And much of my career to that point had been trying to convince them that, no, really, here's a low surface brightness galaxy. They exist. I can show you pictures of them. I can measure these things quantitatively. So it really caught my attention that Milgram was making predictions for this class of galaxies, which at the time were thought not to exist. So basically the data I'm going to show you didn't exist when he made these predictions. He came up with this theory as basically what can we do to change the force law to give a flat rotation curve. The rest of it is basically a genuine prediction, one of which is the Tully-Fisher relation. He had a particular slope that was predicted. Well, that is the right slope. With dark matter, it could have some other slope. It doesn't even have to exist as a relation. The normalization of this depends on the acceleration scale. Fundamentally, in this theory, there's no dark matter, so it's just a change of the force law. So it should be a relation between the stuff you can see, the mass of the stars and the gas, and flat rotation. Well, that's what it is. And the thing that really caught my attention is that it predicted this lack of dependence on surface brightness. This is something that I had predicted there should be a shift for, that I really could not understand the lack of a shift in conventional dark matter terms, and which I think the community still has not really wrapped its head around. But this just falls right out of Milgram's force law. So at this point, I was like, well, that's amazing. Still can't be true, right? So let's check these other things. One thing he predicted in 1983 was that if you computed the enclosed mass to light ratio, how much dark matter do you think you need as a function of radius and surface brightness, that lower surface brightness means lower surface density, which means lower acceleration, which means a greater amount of dark matter that you infer. Not that it's really there, you just infer that because you're in this lower acceleration regime where the effects of the modification to the force law are more pronounced. And sure enough, that's what happens. Same thing for the shapes of rotation curves. Remember, I showed you that beautiful plot with the rainbows from Federico. This is a much earlier version of that, but the same thing happens, that the shapes of rotation curves that Milgram explicitly predicted would behave in this fashion, that the low surface brightness galaxies would have gradually rising rotation curves that only slowly rolled over to V flat, whereas the high surface brightness galaxies would go up fast and maybe even fall a little before flattening. It's exactly what we see. And none of these low surface brightness galaxies were really known at the time. Now, in this theory, there's no dark matter, so a measure of the dynamical mass surface density had better correlate with the surface brightness of the stars you can see. And so that's an attempt to measure that, and that line is not a fit. That's just what has to happen. Again, there's no reason that has to happen in any theory but Mond. So at its root, all Mond is a change to the formula that lets you map from what Newton predicts to what you get. All right, so it amplifies the Newtonian force by an amount that depends on the acceleration. So you go further out, the acceleration drops, the amplitude gets bigger, and this matches up. So when you do this, you can go and fit rotation curves. This was pioneered by my colleague Bob Sanders at the University of Groningen. And you can do this for lots and lots of galaxies. And the only freedom that you have in making these fits is the mass to light ratio of the stars. That is, we see the distribution of stellar light, but we need to know the distribution of stellar mass in order to do the calculation. So this is the one free parameter that is available in making the fits. And so you can do this over and over and over And then you can go out and get a whole lot more data. And these are now fits made by my former grad student, Ping-Fei Lee. And we can do this over and over and over. Mas, 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 mas. All right, we've done this for hundreds of cases now, literally. So here are the residuals of all those rotation curves fits. The color codes the quality of the data. The blue is the best data, green intermediate, gray the worst. The fits are good. There are the occasional goofy case. That's to be expected in astronomy. It would be weird if you didn't have those, but the vast majority of the data are well fit. So that's an important point because each and every galaxy has its own personalized mass distribution. So each and every galaxy is a unique test of this force law that Milgram hypothesized. And it works over and over and over again. So each and every galaxy is an independent test, and the theory captures details that are not explained otherwise. So here's NGC 6946 again. It has a strong concentration of light at the center that causes this little feature here. You can't do that with dark matter. It has to be the stars. Now, it could just be normal stars without dark matter here, but then there are a lot of galaxies like this one, much lower surface brightness, and here's this broad feature in the gas, and that is reflected in the rotation curve. That should not happen if the dark matter is what's doing most of that. The dark matter is completely dominant at this point, and it's arranged in some sphere made of stuff that's not baryonic normal matter at all. They just should not be talking to each other at this level. But you can basically predict, okay, I see this feature. I'm going to observe that feature. And you do over and over and over again. So I've done this exercise where I actually said, let's just close our eyes and try predicting these rotation curves, guessing at the mass to light ratio of the stars, not fitting them, just guessing at them. And so this is for the brightest galaxies, the first one I did. This is my best guess for what the stellar mass ought to be. You apply MOND, and this is the predicted rotation curve. And except for that little bit in the center, it's perfect. No hands. I'm not adjusting anything at all here. If I tried to do this with lambda CDM, well, then there are a lot more parameters I have to worry about, and there are about a dozen different ways you could do this. One I've used here is called abundance matching, which tells you, okay, the stellar mass of the galaxy is so much. That means the dark matter halo mass has to be so much more, and that fails horribly. Right? These are the data. This is the prediction. Now I could go through a menu and start picking some other choice for doing that, but there's no agreement as to how that should be done, and none of them work as well as this crazy theory of Milgram's does. So that's just one case. We can do it for all. Now I have 175 galaxies that I can do this for. And this is the residuals without any fitting whatsoever. These are the corresponding mass to light ratios where I've just assumed that they're all the same, except for some cases with big bulges. With the stars in the bulge should have slightly higher mass to light ratio. So it's basically just going from light to mass to prediction. So it's pretty well. And if you do the fitting, this is what I showed you before, then obviously that tightens up as you'd expect, because now you're adjusting the mass to light ratio a little to compensate. And here are the inferred mass to light ratios. And that's good, because if you know anything about stars, this makes your head explode. There has to be some scatter in this number because there are different kinds of stars in different galaxies. And so this scatter is what we expect, not that. And if you look in other band passes, so that was the Spitzer 3.6 band. If you look in the blue optical band or 2 micron band in the near infrared, you can ask, okay, well, here's the mass to light ratios of these MOND fits. What is the prediction for stellar populations? That is that line. That's what we expect for stars. That has nothing to do with the MOND fits. It's just using what we know about stars to do this. This particular model that I'm showing was made by Eric Bill, wasn't done by me. It just falls right in line. And on top of that, you expect more scatter in this bluer band and in the redder band. And so you can compute what that is. And again, that's what you see.